Continuing with our work with matrices, we're going to look at transformations a bit more. We're going to look at what's called the composition of transformations, and it is an extension on the work we've already done. And let's just try something. You can see we're going to do two things there. Firstly, we are going to reflect the point xy in the y-axis. And then we're going to dilate the result of that by a factor of 2 from the x-axis. So let's do it in two separate parts. So from our previous work, we know that the transformation matrix for reflecting a point in the y-axis is as such. It's negative 1, 0, 0, 1, and the generic point xy is a column matrix. And we can use matrix multiplication to work that out, and you get negative xy, which makes sense because whenever we reflect something in the y-axis, basically the x value becomes the negative of what it was and the y value is the same. Let's then dilate that result by a factor of 2 from the x-axis. So that when it says from the x-axis, remember it heads in the y direction. So we need to put the transformation matrix for part 2 then. So I'm going to, in fact, I'm just going to write then so we can keep up with what's going on. And so that would be 1, 0, 0, 2 from our previous work, and we're dilating that previous result, which was negative xy from just above. And using matrix multiplication, this yields negative x to y. Let's look at the same thing, but in terms of the composition. So, in fact, it's more efficient to sometimes to do that together. Looking at the two transformation matrices, so this one and this one, putting them together as a product and putting the second one first, we would get 1, 0, 0, 2 multiplied by negative 1, 0, 0, 1. Using matrix multiplication, we get negative 1, 0, 0, 2. And now using that with the original matrix, xy, and again using matrix multiplication, we actually get the same result. That's the idea of composition. So the composition occurs right here. Now the order is important, and it's to do with the pre-multiplying you see above. So in summary, we can say that if matrices A and B correspond to two different linear transformations, just like we showed in the example, then AB is the matrix of transformation B followed by A. So notice that it's in the opposite order to the way the two letters of the operations are listed. So AB is B followed by A, and therefore BA would be A followed by B. And we can see how that works in the above example. Let's try one more example that uses this directly. So find the matrix equivalent to a rotation, or find the composition basically. Find the matrix equivalent to a rotation about the origin by 90 degrees. So there's one transformation, and that's anti-clockwise. So I'll underline that as well. And then a reflection in the x-axis. So let's call that one B, and let's call that transformation there A. So we have, for the rotation matrix from our previous work, cos theta, negative sine theta, cos theta, where theta is the anti-clockwise angle. So in this case, if theta equals 90 degrees, we actually have cos of 90 degrees negative 1 times sine of 90 degrees, and cos of 90 degrees which is 0, negative 1, 1, 0. So that is transformation matrix A. And for B, it says a reflection in the x-axis. So we need to recall that reflection in the x-axis. That's where, if you think about a Cartesian plane, reflection in the x-axis, the y values will be the negative of what they originally were in the image. So the object and image have equal but polar opposite y values. The x value is the same if it's reflected in the x-axis. So we have this matrix here, and we can come up with a composition by timesing our result for B and A together. And you know, the order is important because in general, remember, matrices are not commutative for multiplication. Even if they're conformable, doesn't mean that A times B equals B times A. In general, it's not the case. And in this case, it's very true. We have to get the order right. And remember, we established just before that if we have A followed by B, which is the second one, we need to go B times A. Or if it's B followed by A, we need to go A times B. And if we look at this one here, we've got this second one listed will be the first one, so that's followed by that. So that will be the first one listed. And we have the second one listed is the first one that actually happens. Therefore it's B times A. And we do the matrix multiplication. The result of that is 0, negative 1, negative 1, 0. Composition of matrices.